This is a blockchain demo. We're going to do this in a very visual way, though. We're going to make it very easy to understand by stepping through the key pieces of what a blockchain is in a visual way. But before we get started, we need to take a look at this thing that we call a SHA-256 hash. Okay, and a hash, this is one of them right here. A hash looks like a bunch of random numbers. And essentially what it is, it's a fingerprint of some digital data. And it just so happens it's the fingerprint of whatever I type in this box. So if I type my name, Anders, into this box, you see that the hash has changed. As a matter of fact, it changed every time I typed a letter, right? So I'm going to go back to, so it says Anders. Okay, so this is the hash of the name Anders, all lowercase. It starts with 19EA, right? Okay, so if I delete that and I go again, type Anders again, you can see it starts with 19EA, the same exact hash. In that sense, it's a digital fingerprint of this data. Whatever data is here, every time you type exactly the same data, you get exactly the same hash. And I can type anything I want. So you can have nothing, like this, you know, E3B0, that's the hash of nothing. Or you could type tons and tons of stuff. As a matter of fact, you could put like the Library of Congress in here and you would get a hash. And the interesting thing about it is, regardless of if there's a tiny amount of information, no information, or the entire Library of Congress, you're always going to get a hash that is this long, this many characters. You're not going to be able to pre-guess what this is. You kind of have to put the Library of Congress in here to figure out what the hash is, but you'll always get exactly the same hash regardless of how many times you put exactly the same information in. So what I'm going to do is extend this idea of a hash into something that we're going to call a block. All right, so let's take a look at a block. So this is a block, and it's exactly like the hash. It's just that that data section I've broken out now into 3 sections. One called block. This is just some kind of a number. This is block number 1. A nonce, which is just yet another number. We'll go into what that is in a second. And then just some more data, just very similarly to the way that we had it before. However, the hash of this, which includes all of this information up here, is down here, and it begins with 4 zeros. You see that? Okay, that's a relatively unusual hash. You know, most of them are not really going to start with 4 zeros like that, but this one happens to. And because it does, totally arbitrarily, I'm going to say that this block is signed. Okay? So what would happen if I were to change any one piece of this information? Let's say if I were to type something here, right? The hash is going to change. And what's the chance of, if I type letters, this hash is going to start with 4 zeros? Pretty low. It's probably not, right? So let's see what happens when I do that. I'm just going to say, hi. Oh, look at that, right? This hash does not start with 4 zeros. And so the big background here has turned red. So now you know that this block with this information in it is not a valid or a signed block. Okay, and that's where this nonce comes in. This nonce is just a number that you can set to try to find a number that fits so that this hash starts with 4 zeros again. All right, so how do we do that? Well, let's start with 1. Does that start with, no, it's 3, 2, 7, that's not 1. So let's try 2, FF now, 3, 4, 5, 6. You get the idea. Like I could sit here, there's one that starts with a 0. I could sit here all day typing these numbers and trying to figure out one that actually is going to hash out to something that starts with 4 zeros. Gonna take a long time. So here I have my little mine button. I'm sure you've been wondering what happens if I press that. So what's going to happen when I press this mine button is it's going to run through all the numbers from 1 all the way up to try to find one where the hash starts with 4 zeros. And this process is called mining. Let's do it right now. So now it's checking all of the numbers from 1 all the way up. Whoop, there. Now it's stopped at 59,396. And that one just happens to hash out to something that starts with 4 zeros. And it satisfies my little definition of what a signed block is. Okay, so that's a block. Now, can you tell me what a blockchain is? It's probably just a chain of these blocks. Well, how do you put them together? Let's do that. All right, so here's my blockchain. I've block number 1. It has some kind of a nonce just like before. There's some data area to it, but then it has this previous. And here it's a bunch of zeros. Let's roll forward. So this is block 2 and block 3 and 4. This blockchain has 5 blocks on it, right? The previous here starts with 00 AE8, right? Is this number, AE8. And then this previous, B90 is this one over here, B90. So you can see that each block points backwards to the one before it. And you remember that the first block over here, there actually is no previous, so it's just a bunch of zeros. It's actually just a fake number. Okay, so just like we did before, what happens if I change some information here? Right? It's going to change the hash of this block and it's going to invalidate it, right? Well, let's try that. So I'm going to type hi again. Sure enough, that block is invalid. All right, just as we assumed. But what would happen? I'm going to fix that now. We'll go back to something that worked. What would happen if I change something in this block? Right? It's going to change this hash, but this hash gets copied up to this previous. So it's gonna change this one too, right? So it should break both blocks. So let me try typing hi in there, and sure enough, all right? So we can go back as far as we want, to some point in the past and break that block, and it'll break all the blocks since then. Everything before is still green, but this one is red. So if I wanted to, change something in this blockchain, I could just go over to block number 5 right here. We could change it. I'll put hi, and then we could remine it, and pick a different nonce. We'll do that right now, and we could essentially alter the chain. So we've done it, so that we should be good now, right? All right, well, what happens if I go back in time to here and I break it here? Now I have to mine this block, which will pick a nonce that makes this block hash out to 4 zeros, if we can find one. Sometimes it takes a while because it's got to run through a lot of them. There it is. It found one at 138,000. All right, but this one is still broken because although this one starts with 4 zeros, adding the 4 zeros with different stuff up here still makes this block hash out incorrectly. So I also have to mine this block. All right. And that takes some amount of time. That one was a little bit quicker. And then I have to mine this block to fix it. All right. So what we're showing here is that if I go and change this last block, all I have to do is remine this block. If I go way back in time to back here and I make a change like that, I'm going to have to mine this one, this one, this one, and this one. So the more blocks that go by, the more blocks in the past that we are, the harder and harder and harder it is to make a change. And so that's how a blockchain is going to resist mutation, resist change. Okay, so now, I did. If I do this in this block here, you can see that I've changed it to hi and I remined it, blah blah blah. How would I know that my blockchain has been remined? All right, well, let's take a look at that. I'm going to hit this little distributed thing. So now we have a distributed blockchain. It looks exactly like the last blockchain, okay, up to 5. But this is peer A, the first peer. If we go down here, you can see here's peer B, and it happens to have an exact copy of the blockchain. There's actually also a peer C down here, right? And this could go on forever. There's many, many peers out on the internet, and they all have a complete copy of the blockchain. So in this case, if I look at this hash, it's 00E4B, all right? If I go down to this one, I notice it also has E4B. If I go down to this last one, it has E4B, so they must be identical. And I'm going to demonstrate that by going here and typing something. I'll type hi again, and then I will remine this block. And I've got some other number, now it's put some other number up here. So I should be able to mine this block. Okay, now all the chains are green, right? They're all green. However, this chain says the last hash is E4B. The bottom one says that too, E4B. And this middle one here says 4CAE. So I know just by glancing at this one little hash that something is wrong in this blockchain, even though all of the hashes start with 4 zeros. I know that this one is different. And it's different because I have two. It's essentially 2 against 1. We're a little democracy here, right? This guy argues that it's E4B. This guy argues that it's 4CE, it's 4CA, and this one is E4B. So E4B wins. So that's how a completely distributed copy, having a copy on many different computers, they can all very quickly see if all of the blocks are identical. And remember, blockchains can have, 400,000 or 500,000 blocks very easily. So rather than checking through all of them, all you really have to do is look at the hash of the most recent one, and you can see that if anything in the past, anything way back here was altered, you can tell by looking at this at the last block in this in the chain. It's going to hash out to something that doesn't start with 4 zeros and looks very different from what the hashes on the good chains are. Okay, so that's a blockchain. That's the entire thing. There is no more to it than that. But it's kind of not really useful because we don't have something in this data area that means anything. I keep typing my name or hi, and that's sort of irrelevant information. So what we really want is a token. So let's do a token on our blockchain. All right, now look at this. So I have this token just totally arbitrarily. I'm calling these, I guess, dollars, right? So we have $25 from Darcy to Bingley. $4.27 go from Elizabeth to Jane. You get the idea. It's basically there's all these transactions that are happening. And I've just replaced the data with these transactions. And just like we saw before, so there's multiple blocks here. This one has more transactions. It doesn't matter how many transactions there are. There can be many or there can be few or none. If we keep going forward in here, just like we saw before, if we go down, we notice we have all these other copies of the same blockchain, right? So now here's where the immutability is important. If I change something back here, you'll notice that this is, A7FC, blah, blah, blah. It's something else. So it's something different than what's down here. So in this way, it's very important that if I were to go back in time and change some value that we would notice. It's very important with money that you don't lose track. And that's the whole point of using a blockchain here. This is the whole point of resisting any kind of modifications, of things that have happened in the past. So that's the reasoning behind using a blockchain to remember tokens. Now, one thing I would mention here is that we're not listing, Darcy has $100 and he's giving 25 of it to Bingley. The only thing we're saying is Darcy gives 25 to Bingley. We're not remembering a bank account balance. We're only remembering money movements. So this begs the question, does Darcy have $25? Well, we have a problem here in this version of the blockchain. We don't actually know if Darcy has $25. So let's look at a Coinbase transaction. So if we look back here, a Coinbase, we're going to add a Coinbase transaction to our blocks. And this is very similar to what we've seen before, but we're just adding a Coinbase at the top. And what that's saying is we're going to invent $100 out of thin air and give it to Anders. Okay, there's no transactions in this block because nobody had any money previous to this. In the next block, another $100 comes out of nowhere and goes to Anders. I'm a fan. I love it, right? I'll take $100. Now we have some transactions. You can see that they're all from Anders. They're all from me because I'm the only one who has any money at this point. So I'm sending 10 of my dollars to Sophie. Do I have $10? Yeah, I do. I look back and I see that this Coinbase transaction has given me 100, so I have at least 10 and I can send it on. And you add all these up and they don't go over 100, and it follows sort of a basic rule of a currency. Like, you can't invent it out of thin air. You can't create money out of thin air. Its dispersion is controlled. So now if we look at this blockchain that we've created and we zip forward in time and we notice that we see that Jackson is giving Alexa $2. And so does Jackson actually have $2 to give Alexa? Well, we go back a block before and we see that Emily, who had gotten $10 from Anders, gave 10 to Jackson. And so Jackson does have the money. So we can just go backwards and find that out. And that's actually one of the benefits of having a previous here. It's easy to go backwards. We just look for the block that looks like that has that hash. And here it is right here, right? So it points to blocks back in time and allows us to trace the provenance of any coin that we want. So that's a basic blockchain, and we're running a currency on top of it. And as you know, blockchains there are many copies. Everybody has a copy of it. So if we mutate, this and make it $6, these go invalid. It does not agree with these blockchains down here, these copies of the same blockchain down here. So this resists tampering, which is what you want for a currency. It works very well for things that are small and transactional like this. I'll go ahead and fix that. And they're just a very efficient way to handle agreement on what has happened in the past. It's kind of this immutable history that goes down with time. So that's a basic blockchain and a token on it. We're glossing over some main points, but if you dig into the demo and click through these things and play around with it, you get a better and better idea of how this works. There will be a part 2 where we go into a little bit more detail about how the transactions are created. Till then.
Encryption is the process of taking a message and scrambling its contents so that only certain people can look at your message. There are 2 types of encryption: symmetric and asymmetric encryption. Let's first take a look at symmetric encryption to understand why asymmetric encryption was created. To do that, let me introduce you to Alice and Bob. Alice has a sensitive document that she wants to share with Bob. She uses an encryption program to protect her document with a password or passphrase that she chooses. She then sends the encrypted document to Bob. However, Bob cannot open this message because he doesn't know the passphrase that Alice used to encrypt the document. In other words, he doesn't have the key to open the lock. Now comes a real problem. How does Alice share this passphrase securely with Bob? Sending it through email is risky because others might find the passphrase and use it to decrypt any messages between Alice and Bob. This is exactly the kind of problem that asymmetric encryption intends to solve. It is comparable to a mailbox on the street. The mailbox is exposed to anyone who knows its location. We can say that the location of the mailbox is completely public. Anyone who knows the address can go to the mailbox and drop in a letter. However, only the owner of the mailbox has a key to open it up and read the messages. So let's now go back to technical details. When using asymmetric encryption, both Alice and Bob have to generate a key pair on their computers. A popular and secure way for doing this is by using the RSA algorithm. This algorithm will generate a public and private key that are mathematically linked to each other. Public keys can be used to encrypt data, and only the matching private key can be used to decrypt it. Even though the keys are linked together, they cannot be derived from each other. In other words, if you know someone's public key, you cannot derive his private key. If we retake our mailbox example, then the mailbox's address would be the public key, something that everyone is allowed to know. The owner of the mailbox is the only one who has the private key, and that is needed to open up the mailbox. Let's now take a look at how Alice and Bob can use asymmetric encryption to communicate securely with each other. They start by exchanging their public keys. Bob gives his public key to Alice, and Alice gives her public key to Bob. Now Alice can send her sensitive document again. She takes the document and encrypts it with Bob's public key. She then sends the file to Bob, who uses his private key to unlock the document and read it. Because they use asymmetric encryption, only Bob is able to decrypt the message. Not even Alice can decrypt it because she doesn't have Bob's private key. The strength and security of the asymmetric encryption now relies on Alice and Bob to keep their private keys well protected. If an attacker steals Alice's private key, it can be used to decrypt all messages that are intended for Alice. However, the attacker cannot decrypt messages that were sent by Alice because that requires Bob's private key. Asymmetric encryption is used in a lot of places where security really matters. You might not be aware of it, but every time you visit a secure website via HTTPS, you're actually using asymmetric encryption. It's also being used to securely send emails with the PGP protocol. And one last example, Bitcoin also uses asymmetric encryption to make sure that only the owner of a money wallet can withdraw or transfer money from it. So now you know how asymmetric encryption works and what the differences are between asymmetric and symmetric encryption.
Welcome back. Last time we looked at a blockchain and how it works, particularly in the financial context. And we have these transactions that we were creating that move money from one person to another. But there's a big problem with this, and that is what's to stop somebody from just adding a transaction that spends all of someone else's money to them. There seems to be no protection here for that. So what we're going to do is we're going to look at ways to add transactions to a blockchain that keep it so not just anyone can create these transactions. In order to do this, we need to look at another cryptographic primitive, and that is public-private key pairs, and then we'll use that for signatures. So let's take a look at that right now. So here's a public-private key pair. The private key here, it's just, it's a really, really long number. And any number is a private key, right? You could make this be 1. 1 is a private key. It's not a very good one. Lots of people have thought of the number 1 before. But you could, you could pick some really, really long number, and it's sort of a random number, and we can use that as a private key. Now you see every time I'm adding digits here, it's recomputing the public key that relates to that private key, and that's why the stuff down here starts changing. So as the name would imply, this private key is to be kept private. Only you have this private key, and you never tell it to anyone else, okay? And just as the name implies, public key, the public key here, you just tell everyone. This is something that you want everybody to know. This is something that there's no harm in letting everyone know. There is not a way to derive from this public key what the private key is, okay? So it's just a kind of a public version of this private key that does not reveal what the private key is. Okay, so I'm going to hit my little random number generator, so I get a nice really long private key, and it's not something where the numbers are close together where I typed on the keyboard. It's something a little bit more random looking. And then the system has derived a public key from this. So this is going to be my private key, and I'm going to use this to do signatures. So let's do that right now. So here's a message signature. So here is a message. I'm going to type, hello, Anders, that's me. And I have my private key here, 656, whatever it is. This is my private key. Only I have that. And here's the message that only I have. And I can hit sign and come up with a message signature here. Now this message signature I can pass to someone else. I'm going to hit my little verify button. I'm going to pass this message signature to someone else, to anybody else. Okay, now of course they don't have my private key because I keep that private and nobody else can see that. But I publicize my public key and they know that everybody knows that this is my public key. So given this message, and everybody knows my public key, and given the signature that I just made, you should be able to verify this. Now, of course, if I hit verify, sure enough, the screen goes green. This is a valid message, and I have verified that whoever signed this message and came up with this signature had access to the private key behind this public key. Okay, and if I have kept that private key secret, that must be me. Okay, so that's a message signature and how you can sign something and verify it. Now, instead of just using this freeform text box, let's put some structure around this. I'm going to make a transaction here instead. All right, this is similar to what we saw before. The message I'm going to say is I'm going to send $20 from, this happens to be my public key, to somebody else's public key, whoever this is that I'm sending money to. Okay. I, of course, because I'm signing this message, I have my private key. I never tell anybody the private key, but I can use this private key to sign this message, which consists of these three things up here. And if I hit sign, I get a message signature. Great. All right. Now, I send this whole thing out. I send out my message and my signature to somebody else. And they know that I'm trying to send $20 from my public key to this somebody else's public key. And you'll notice this little blue box around the from public key. That suggests that you can check this signature against this public key to see whether or not the private key behind this public key actually signed this message. So let's hit verify. Sure enough, it verifies. So I know that the person in possession with the private key behind this public key, must only be Anders, is sending $20 to some other public key. Okay? Now, let's use this in the blockchain. Let's go back to the blockchain case that we were looking at before. Now, you'll notice a couple of different things here, all right? First of all, there's not names here anymore, right? They're just public keys in the from and the to. And you'll also notice that I added a signature section here, okay? So in this case, this is this public key sending $2 to this public key. And here's a message signature that says that it is. Well, what happens if I change this to, $25? Okay, of course it broke the block, but it also broke the signature. The signature is not verified, and that's why the signature is turning red. So while we could press the little mine button, a miner could take this altered block and remine this block, they're going to end up with something where the block is signed, which should eventually happen. And there we go. And the signature, though, is still invalid because the miner they don't have my private key. They only have my public key, so they can't come up with the right signature. Okay, so that's the way we can make sure that the message, this transaction here, was posed by the person that had the money, and only that person, not just anyone else on the internet. So that's how public-private key pair message signing is used to protect transactions and make sure that they are from the people that they proposed that they're from. Now, if you think about it, it actually works really well because in order to create a new address, a new public key, the only thing you have to do is go back
and come up with a new private key, a new random number. You didn't have to go to a centralized authority to come up with a public-private key pair. You just make up a private key and you use it. You derive the public key from it and you put that out there, and that's how people can pay you. So that's a blockchain. Again, it's a financial context. All successful production blockchains that are distributed use a token of some sort. So they all have a financial context. So that's how a blockchain will work. I mean, I have glossed over a couple of the details, but for the most part, the overall idea here that you're looking at is very similar to the way that Bitcoin works, and many other cryptocurrencies as well. So that's a blockchain. I hope it's helpful.
Blockchain, the hype word of 2018. But do you know how a decentralized peer-to-peer system with no authoritative figure makes decisions? The answer lies in consensus mechanisms. There are various consensus mechanisms, but they all serve the same purpose: to ensure records are true and honest. The difference is the way the consensus is reached. Here, we will explore 3 types of consensus mechanisms. First, let's take a look at proof of work. In a proof of work system, transaction data is stored in blocks, validated by having people solve a complicated math problem attached to it. This is typically done by powerful computers and is known as mining. A reward in the form of a cryptocurrency is issued to the first miner who cracks the problem. Lost? Well, let's break it down. Imagine a group of treasure hunters trying to open a chest with a complicated lock attached to it. Figuring out the correct combination is tedious, but the first person to do so gets rewarded. Simply put, proof of work is a race to figure out the right combination on a treasure chest. Cryptocurrencies like Bitcoin and Ethereum use the proof of work mechanism. Next, we have proof of stake. Here, the creator of a new block, also known as a validator, is randomly chosen based on how much stake they commit to the network. Meaning to say, the higher the stake placed, the higher the chance to be selected as a validator. Let's apply this to the treasure chest scenario. Picture a group of treasure hunters vying for a chest. The chest is rewarded based on a lottery system. To participate, each hunter has to buy lottery tickets. The more each hunter buys, the higher the chance of winning. Blockchain protocols like Cardano's Ouroboros and EOS adopt the proof-of-stake consensus. Lastly, proof of authority. A modified form of proof of stake, here only approved parties selected based on their reputation can become validators. Let's revisit the treasure chest scenario. The group of treasure hunters form a union and pool their treasures. Based on their level of trustworthiness, a select few are appointed by the group to ensure the validity of the chest's content. IBM's Hyperledger Fabric and Ethereum's Kovan testnet are some examples of blockchain systems that use proof of authority. Whilst traditional blockchain companies exist on a single consensus mechanism, some innovative ones are adopting multiple consensus protocols. Take OPED Foundation, for example, who is building a unique blockchain to store data collected on its Tuition Companion chatbot app by applying both proof of authority and proof of work protocols. Data, such as students' academic, extracurricular, and personality profiling records are stored on the blockchain and potentially validated via a proof of authority framework powered by Hyperledger Fabric. Validators in this instance are reputable educational institutions or even national registrars and respective ministries of education. This helps ensure that all student data is trustworthy. But who will work for free? Proof of work consensus thus comes into play to reward validators who have performed work. With Hyperledger Fabric, each student record is secured with a private hash key owned by the student. The data can only be accessed when the students provide the unique key. This means student privacy is preserved and controlled by the student themselves. For example, when students apply to university via OPED's platform, they will provide the unique key of their records to the university. With that, the university will be able to access their latest academic records. Students will also be able to see if their records have been unlocked or at least considered for application. This boosts efficiency and transparency compared to traditional methods. By marrying the proof of work and proof of authority models, OPED Foundation's blockchain solution ensures privacy on students' data while incentivizing both educational institutions and students when they contribute to OPED's platform. With blockchains gaining popularity, it's only a matter of time before we see even more unique hybrid systems created.
Hey there, my name is Xavier, and you might have read articles online saying that cryptocurrencies like Bitcoin uses enormous amounts of electricity to secure their networks. But why is that? And more importantly, what are the alternatives? Mining new coins takes a lot of computing power because of the proof-of-work algorithm. The idea was first introduced in 1993 to combat spam emails and was formally called proof-of-work in 1997. However, the technique went largely unused until Satoshi Nakamoto created Bitcoin in 2009. He realized that this mechanism could be used to reach consensus between many nodes on a network, and he used it as a way to secure the Bitcoin blockchain. However, the proof-of-work algorithm works by having all nodes solve a cryptographic puzzle. This puzzle is solved by miners, and the first one to find the solution gets the miner reward. And this has led to a situation where people are building larger and larger mining farms like this one. According to Digiconomist, Bitcoin miners alone uses about 54 terawatt hours of electricity, enough to power 5 million households in the US or even power the entire country of New Zealand or Hungary. But it doesn't stop there. Proof of work gives more rewards to people with better and more equipment. The higher your hash rate is, the higher the chance that you'll have to create the next block and thus receiving the mining reward. To increase chances even further, miners can come together in what's called mining pools. They combine their hashing power and distribute the rewards evenly across everyone in the pool. So, to sum it up, proof of work is causing miners to use massive amounts of electricity, and it encourages the use of mining pools, which makes the blockchain more centralized as opposed to decentralized. So to solve these issues, we have to find a new consensus algorithm that is as effective or better than proof of work. In 2011, a Bitcoin Talk forum user called Quantum Mechanic proposed a new technique that he called proof of stake. The basic idea is that letting everyone compete against each other with mining is just wasteful. So instead, proof of work uses an election process in which one node is randomly chosen to validate the next block. Oh yeah, small difference in terminology here. Proof of stake has no miners, but instead has validators. And it doesn't let people mine new blocks, but instead mint or forge new blocks. Validators aren't chosen completely randomly. To become a validator, a node has to deposit a certain amount of coins into the network as stake. You can think of this as a security deposit. The size of the stake determines the chances of a validator to be chosen to forge the next block. It's a linear correlation. Let's say Bob deposits $100 into the network while Alice deposits $1,000. Alice now has a 10 times higher chance of being chosen to forge the next block. This might not seem fair because it favors the rich, but in reality it's more fair compared to proof of work. With proof of work, rich people can enjoy the power of economies at scale. The price they pay for mining equipment and electricity doesn't go up in a linear fashion. Instead, the more they buy, the better prices they can get. But back to proof of stake. If a node is chosen to validate the next block, he'll check if all the transactions within it are indeed valid. And if everything checks out, the node signs off on the block and adds it to the blockchain. As a reward, the node receives the fees that are associated with the transactions inside this block. Okay, but how can we trust other validators on the network? Well, that's where the stake comes in. Validators will lose a part of their stake if they approve fraudulent transactions. As long as the stake is higher than what the validator gets from the transaction fees, we can trust them to correctly do their job. Because if not, they'll lose more money than they'll gain. It's a financial motivator and holds up as long as the stake is higher than the sum of all the transaction fees. If a node stops being a validator, his stake plus all the transaction fees that he got will be released after a certain period of time. Not straight away, because the network still needs to be able to punish you should they discover that some of your blocks were actually fraudulent. So the difference between proof of work and proof of stake are quite significant. Proof of stake doesn't let everyone mine for new blocks and therefore uses considerably less energy. It's also more decentralized. How is that? Well, in proof of work, we have something called mining pools. Those are people who are teaming up to increase their chances of mining a new block and thus collecting a reward. However, these pools now control large portions of the Bitcoin blockchain. They centralize the mining process, and that could be very dangerous. If the 3 biggest mining pools would merge together, they would have a majority in the network and could start approving fraudulent transactions. Another important advantage is that setting up a node for a proof-of-stake based blockchain is a lot less expensive compared to a proof-of-work based one. You don't need expensive mining equipment, and thus proof-of-stake encourages more people to set up a node, making the network more decentralized and also more secure. So the 51% is actually less likely to happen with proof-of-stake. But that's not the only risk. Proof-of-stake algorithms also have to be careful how they select the next validator. It cannot be completely random because the size of the stake has to be factored in. But at the same time, the stake alone isn't enough because that will favor rich people who will get chosen more frequently, will collect more transaction fees, become even richer, and thus increase their chances of being chosen as a validator even further. There are a number of proposals to fix this, like CoinAge-based selection, for instance. Another potential problem is when the network chooses the next validator, but he doesn't turn up to do his job. This could easily be solved by choosing a large number of backup validators as a fallback. In short, alright, so now that we know what proof of stake is, what benefits it has,